All life that we know lives in this one beautiful oasis floating in space. But the Earth is not alone. We live in a unique two-world system. The Earth's silent companion played a pivotal role in the emergence of life on our world and is the key to our exploration of the universe. Behold, Earth's offshore island, the Moon. The Moon was probably the first celestial object that you learned to identify in the night sky. And it's not only people who notice it. Who hasn't heard of dogs baying at the Moon? Other species also seem to have an interest in lunar matters. During the 1960s, the Moon was the goal in a race between the United States and the Soviet Union that gave us the capability to live and work in space. When Buzz Aldrin and Neil Armstrong landed on the Moon, that race was won. But the science had just begun. In a few moments, we'll look at some of the centuries-old mysteries solved by the Apollo program and how that knowledge will benefit everyone on Earth. Moon-bound astronauts provided the first spectacular images of our world from space. These pictures helped create the present global environmental movement as we became conscious of the fragile nature of our planet. What many people do not realize is that the Earth is intimately connected with the space environment that surrounds it. For example, nearly all of our energy comes directly or indirectly from the Sun. One of the most profound influences on the Earth is the gravity pull of the Moon. The most graphic illustration of this influence is ocean tides caused by the pull of the Moon and the Sun. Biologists believe that tidal pools are ideal locations for the development of the first life on Earth. The gravitational pull of the nearby Moon, and to a lesser extent the much larger but more distant Sun, tug on the world's oceans, causing rising and falling local ocean levels. Sometimes the Sun and Moon are on opposite sides. The Moon orbits the Earth every 29.5 days, so some of the time the Moon and Sun's pull are in different directions. The Moon has greatly influenced all cultures here on Earth. It's no surprise that we call the 30-day cycles of the year months, a word directly derived from the word moon. It's not just the West that has developed these. The Chinese character for month is directly derived from the moon. How big is the Moon compared with the Earth? You probably have two objects at home that are almost exactly the proper Earth-Moon scale. The Moon's diameter is 27% that of the Earth. If you use a regulation basketball to represent the Earth, the Moon is about the size of a tennis ball. The Moon's actual diameter is 2,160 miles, a bit less than the width of the continental United States. The total surface area of the Moon is similar to that of the African continent. Some people refer to the Moon as the 8th continent of the Earth. If you or your neighbors have a satellite dish, it points to one of those 400 white dots that make up this big ring around the Earth. If we move up and look down at the Earth, from the North Pole, we see that satellites in geostationary orbit are about 24,000 miles above our planet. At this altitude, it takes each satellite 24 hours to orbit the Earth. Since that matches the Earth's rotation, you can point the satellite dish once, and it stays pointed to the particular satellite. If you take your basketball and wrap a string around it once, that's pretty close to the geostationary orbit altitude. But it's only about 1/10 of the way to the Moon. It would take almost 10 complete wraps of string around your basketball for a distance of about 27 feet to show the average Earth-Moon distance of 240,000 miles. So your tennis ball and basketball have to be a lot farther apart than most people would guess. Try this out on your friends and let them guess what the proper scale distance should be. Another way to think about the distance between the Earth and the Moon is that it takes light 1.3 seconds to travel between the two, or 2.7 seconds round trip. Compare that with the 8 minutes it takes light from the Sun to reach the Earth, and you realize that the Sun is about 1,000 times further away from us than the Moon. Since the Apollo program and the first Earth Day, we've come to realize that our planet is facing very significant pressures. As we share this world with more and more people, the consequences of burning fossil fuels for energy are beginning to threaten the biosphere. The growth of energy use is greatest in the Third World, where people are moving into cities. If the folks in these countries use even a small fraction of the energy levels that people in North America enjoy, there will be even greater pressure from the byproducts of fossil fuels. But our local star, the Sun, bathes the Earth-Moon system with enormous amounts of power. Every square meter of surface area in the neighborhood of the Earth and Moon sees enough power to light up 13 big 100-watt light bulbs plus one little 60-watt light bulb all the time. For more than 30 years, NASA and the Department of Energy have explored ways to use that energy from the Sun. By putting solar collectors in 24-hour orbit around the Earth, we could get clean energy without CO2 or radioactive byproducts. The technology required to do this has been successfully tested for decades. Each such satellite could power a city the size of St. Louis or Chicago, and at night, when energy demand for homes and factories is low, the power could be used to split water into hydrogen to fuel our vehicles. So why haven't we done this yet? Because the cost of launching the construction materials at present prices is far too great. The early solar power satellite studies considered using very large rockets that would even dwarf today's space shuttle to launch construction materials from the Earth. But the Earth is not a very good place to start if you want to build big things in space. To find the best source of materials for space construction, let's consider a new way to view the solar system. We'll turn it on its side and imagine that it is a giant table. Wells in that table show the energy needed to get to space from the Sun, planets, and other bodies. Massive objects have deeper wells. This diagram shows the Earth's deep gravity well. To launch things requires climbing out of that well to get to the plateau of free space. But the nearby Moon is in a tiny gravity dimple. If the Earth's gravity well is 22 steps deep, the Moon's gravity dimple is only one small step deep. It's much easier to bring the raw materials for space construction downhill from the Moon than uphill from the Earth's surface. Another way to appreciate the relative ease of launching from the Moon is to look at the huge Titan rocket used to launch 2 astronauts in the Gemini spacecraft. By contrast, it only took the top half of the lunar module to launch 2 Moon astronauts and hundreds of pounds of rock into lunar orbit. We know what most of the Moon is made of because we've been there and brought samples back to study. It's a surprise to most people to learn that more than 40% of Moon soil is oxygen. There's plenty of silicon to make solar cells to turn sunlight into electricity. Metals like aluminum, iron, and magnesium are abundant, and there are some very interesting herbs and spices present. In 1998, the Lunar Prospector spacecraft detected large amounts of hydrogen when flying over the permanently shadowed regions at the Moon's north and south poles, suggesting that ice might be there. This discovery set off a new moon rush, with lunar probes from nations now at the Moon, like this European Ion Engine probe, or planned for the future. Russia, India, Japan, China, and the United States all have new prospecting spacecraft in the works. Let's look back for a moment at the first human voyages to the Moon.